Happy rain and ice day, calculus kids. Let's work on our first lesson that will be for after the quiz. Right, this new topic called slope fields will not be quizzed tomorrow. We still are going to have our quiz tomorrow because you've done all the review. Mr. Davis's classes, if you're watching this, he already taught this lesson, but you will need the review. I don't know if he gave it to you or not. The differential equation in Euler's method review key is on Canvas, and so are the solutions. You still might want to practice some more separable differential equations, either from homework or classwork. And of course the very first lessons that we did that had a book assignment with position, displacement, distance, and those were handouts 1, 2, and 3. So for Mr. Chase's and my classes, this warm-up does practice something that could be on the quiz. Remember, the quiz will be without the calculator. So when I ask you a question like this, what I'm looking to grade, and this I think was number 44 from last night, when I'm looking to grade this, notice I give you how many steps I want, which I didn't really have to do if I give you the approximating value and delta x. Whether you set this up with equations or the table, the only thing that is going to be graded so I'm going to do if you use the table, what would be on the rubric for this would be, do you recognize that you're starting at 1, that the derivative at the initial condition is 2 times 1 minus 0, which is 2, multiply by dx to get dy. So if you're multiplying dy dx, which is 2 times 0.1, you of course get 0.2, and then you are adding the old y and the change in y to get the new y. Then your next row is going to be from 1, you're going to add delta x, not multiply. Here you're multiplying by dx, here you're adding dx, so I get 1.1. And then I'm using my new y of 0.2. I'm not really going to look here or here. Here's what's going to be graded. Your first run through, do you have some work in here? Not really looking too closely at it. And then, what is your final answer here? What is your approximation when x is 1.3? And of course, if you're doing this with an equation, right, you're doing the tangent line, the old y plus the slope at the x and the y times dx. Plus the new slope and again, not really looking here or here, but your last run through. This will, so your first run through and your last. And what will happen is if this is right and this is right, but your answer is not right, what I will do then is I will look back at the inside work and see, can I find a place where you made a simple mistake so that I can give you follow-through points. Okay. This handout I just made visible on our Canvas site. Right, it is the next handout in the line. This will be checked on Friday. Alright, so, new topic. Euler's method is a way of approximating solution to a differential equation or initial value problem by using little slope lines, really. And it gives you approximate points on the graph of a solution. And remember, I showed you a couple of examples where you can see that with the delta x's we were using, the approximations weren't that great. I can kind of use the same idea to create a field of equations called a slope field, sometimes also called directional fields. They are very easy to create with a computer or the calculator. As a matter of fact, I've given you a program that we're not going to use today because slope fields on AP, you'll have to draw your own, and will probably be on a non-calculator portion. So the first lesson is going to be without the calculator, and then on Friday I'll show you how to supplement what we're doing with the calculator. So it does use the derivative because you're given a differential equation, the assumption being that you can't or don't want to take the time to solve a complicated differential equation. But we use a number of points, not just the initial condition, and we draw little lines. They're cute. I'll show you what I mean by that. Alright, so just watch this. So given a differential equation, that I can solve. This doesn't even take separable, right? I know the solution to this is y equals x squared plus c. Shh. Don't tell anyone. Pretend I don't. If the differential equation is 2x, I say to myself, I wonder at the point 0, 0 what the slope is. So of course, since the derivative only depends upon x, the slope only depends on the x-coordinate, I really don't care about, but I still want you to focus at the point 0, 0. The slope is 0, and I want you to draw a cute little tangent line with a slope of 0 through the point 0, 0. So this is the point, this is the slope. See what I did there? I drew a little cute line segment with a slope of 0. Then I moved, it's cute. I moved to the point 0, 1. Well again, since the slope only depends upon x, who cares what the y value is? The slope is still going to be 0, isn't it? So through the point 0, 1, guess what I'm going to draw? Yep. And what do you notice? At every x value of 0, the slope is 0, right? I'm going to draw a horizontal line segment because these didn't matter. And the only reason they don't matter is because of the differential equation. The slopes are 2 times the x-coordinate. 2 times the x-coordinate. So wherever x is 0, the slope is 0. So hopefully you can see where I'm going to go from here, right? What about when x is not 0? How about at the point 1, 0? So what about here? What is the value of the slope? Now you took Algebra 1. What does a line that goes through the point 1, 0 and a slope of 2 look like? And this is just an approximation, so stop, I don't want anybody to, this is what you did in Algebra 1, right? Compare, draw the line y equals x, and then draw the line y equals 2x, and talk about it. It's a little bit steeper than normal. Do you remember that? Guess what's true at 1, 1? And guess what's true everywhere x is 1? Again, because of the differential equation, the y values don't matter to the value of the slope. So all points where x is equal 1, I will have a slope of 2. See where I'm going here? What kind of line segment are you going to draw at the point 2, 0? It is going to be a line segment. It is going to have a positive slope, but it is going to be what compared to the lines going through 1s? That's right, steeper. And yes, all the way, because the y value doesn't matter. It only took me 1 to see the pattern. Get it? Math is patterns. What do you think is going to happen when I make x negative? Gee, look at this symmetry. When x is equal to 1, the slope is 2. When x is equal to negative 1, the slope is, Wow. Now I've been dropping little clues for you all the way along. This is called a slope field. Congratulations. Now I did just ask you to watch this one, but now I want you to kind of look at this and kind of look at it in its entirety. I don't know if any of you are old enough for those Magic Eye books where you would look at a page and it was drawn all these little teeny pixels, and if you kind of crossed your eyes and refocused or whatever, you would see a 3D image popping out at you. Well, there's no 3D image going to be popping out of this, but I want you to see if you can find a pattern representing the solution to the differential equation. X squared, you know what that looks like, plus a vertical shift. This is what it really looks like, right? A whole bunch of them. Can you see this picture over here? These directional slopes guide solution drawings. I see x squared plus c. See what I did there? There's your first slope field. So, if you know an initial condition, so I didn't give you an initial condition first, but now I have. If I give you an initial condition of 1, negative 2, you can, and this is what AP is going to ask you to do, not only create a sketch slope field, but sketch a particular solution through it. 1, label the point. Make it obvious, just in case you're wrong. Obvious. Then, from this line, from this point, you should know for this one what it looks like, right? It's a parabola, but use the directional lines to guide you. When you go to the right, it's saying the curve has a slope that is positive, and then as you move further right, it's getting more positive. They want you to draw a smooth line. Nice rule of thumb: don't cross slope lines, right? Let them guide you. So my slope lines are guiding me to make a curve whose slope increases as x increases. But here, as x increases, the slopes are getting lower and, as a matter of fact, approaching 0. Here, the slopes are negative and getting more and more negative. Okay, that's kind of terrible. You're going to get, AP is going to forgive you for a lot of your mistakes, but here's what you're going to, here's how you get something, here's how you get one wrong. Like that, or God forbid, like that, right? Something nice and smooth. Using the slope fields, the slope field line segments to guide your direction. And it is a rough picture. And this should say solution curve. So what if I asked you to sketch the particular solution through the point 0, 1? Mark it. Slide. Alright, let's do one of, now you do this one. So we're going to draw cute little slopes. Given the differential equation cosine x, you know what the solution is. So, at 0, pretending I didn't know the solution was sine x plus c, knowing the derivative is cosine of x and only depends upon x. Again, I make note to myself, these are thoughts that I have. Remember, I wouldn't really be able to, there's a lot of differential equations that you won't be able to know this, but we're going to practice with ones we know. So if the derivatives only depend upon the x-coordinate, the slope's at 0, well, what is cosine of 0? At every x I can, whoops, cosine of 0 is 1. At every x-coordinate, I drew a 1. Now, I didn't pick, I wonder what the derivative of 1 is. At 1 is. I didn't pick that because I don't know what the cosine of 1 is. But, guess what I do know? I know values of pi. What is the cosine of pi? And what is the cosine of negative pi? Right? Cosine of pi is negative 1, and so is the cosine of negative pi, right? Unit circle values. So I made this value pi and negative pi. And this is, of course, at 0. Gee, what other number do you think I'm going to pick? Right? At all the pi over 2's, right? Zero, right? No matter where, right? At pi over 2, negative pi over 2, 3 pi over 2, 5 pi over 2. So now I have 0, pi over 2, pi, 3 pi over 2. Look at that slope field. Look at, can you step back and look at that slope field? Right, and then of course I drew lastly I drew cosine of plus and minus 2 pi, of course, is 1. Right? So there's all my slopes of 1 at 2 pi and negative 2 pi. Can you see the solutions, all of the solutions plus c, right? Can you see that at 0 I should have a curve with a slope of 1. That curve should go up and approach a slope of 0. Slopes be negative and approach negative 1. And then at negative 1, right? Crazy. Looking at a slope field can show me a family of curves. So if you get out your calculator, we know what the solution really is. So if you put sine x plus L1 into your calculator and put negative 3 to 3 into L1 and then look at it, and again, you can also just watch me do it. There's sine x plus L1, and into L1 I put negative 3 to 3, and when I hit a zoom 6 window, which goes from negative 2 pi to 2 pi, you can see all the solutions from negative 3 to 3 that would sweep through that slope field you just drew. Right? And of course there's an infinite more. So I want you to look at this picture and break it up. Right? Can you see all those slope lines at every x? Right? For instance, when x is equal to 0, all of these slopes are 1 because the cosine of 0 is 1. At all the maximums here, wherever x is pi over 2, the slope is 0. Where an x is pi, because the cosine of pi is negative 1, the slope of every one of these curves is negative 1. Oops, sorry. The cosine of 0 is 1. This is the slope field of the solutions to the differential equation cosine x. Things to start thinking about is, since all of the slopes are exactly the same vertically, that's a clue that the derivative should have no y in it. So ask yourself, I wonder what a slope field looks like if there is an x and a y in it. Or what if there's only a y in the differential equation? I wonder what pattern I would see. Let's draw some more little slopes. 2x minus y. Remember that was the from the warm-up. So we used Euler. So our old objective use Euler's method to approximate a point on the solution. I guess you could say however many times you used Euler's method, you had 3 or 4 points. New objective, use or sketch a slope field to see graph of the solution plus C. Get it? So this is actually, the reason this has a 32 next to it is because I'm actually doing one of the problems on the handout. And I designed the handout, from book problems but I wanted to capture the graphs that are used, because we've seen AP, when they ask you to draw a slope field, this is how they've started to try to do it so that they don't get a whole bunch of different looking graphs. This is a way that they've tried to standardize when students have to draw their own slope fields. So they give you an axis with these dots in them, and take those dots to mean that's where they want you to draw line segments. So when I'm asked to draw a slope field representing the solutions to this differential equation, I make myself a chart, and these are all the points on it. So I might start and say, for instance, I might start at maybe the left top. So I might say -1, 2, and -1, 1, -1, 0, and -1, -1. And that's going to give me all the slopes and all the points where I have to draw line segments. Then I'm going to go get the slopes from the derivative. So I'm going to take this, and notice the slopes, every slope at each point is 2 times the x-coordinate minus the y-coordinate. Question I might ask myself, where will the slopes be horizontal? Before I even start, where will I have horizontal slopes? Where the slope is equal to 0. So where is 2x minus y equal to 0? Every time y is equal to what? Twice the x-coordinate. Can you see where that might happen? How about this? Question. Where will slopes be negative? How about positive? And I've taken care of all the real numbers, haven't I? I might also think about things like, where are they most steep? Where are they most flat? Stuff like that. These are all things that I have to train myself to start thinking when I'm looking at a differential equation and a slope field, and reading and interpreting a slope field. Because right now we're just going to drawing them. Next we're going to go to interpreting one. Like, what if I'm given a slope field? Can I get information about the differential equation, right? But right now we're just going differential equation to slope field, right? So we're just starting. So what is 2 times -1 minus 2? 2 times -1 minus 1, 2 times -1 minus 0, and 2 times -1 minus -1. So -2 minus 2 is also known as -4. Check my math here. -2 minus 1 is -3. -2 minus 0 is -2. And -2 plus 1 is -1. So I'm going to draw a slope that is negative and steep here. Negative but less steep here. Negative and less steep here. And negative, and try to go through this at 45 degrees here. Right? And then I'm just going to repeat. Okay, so you should be doing this. If you haven't already, maybe downloaded the handout. So of course now I'm going to do when x is equal to 0. Ooh, horizontal tangent. So at, oh crap, did I do that wrong? I did the other ones wrong, didn't I? Sorry. Oh no, I didn't. Ah. At -1, 2, it was -4. Ah! Alright, so at 0, 2, it's -2, so that should be, right, similar to that one. -1 should be 45 degrees. And then +1. So as you can see, this is a little tedious, so you hope they don't give you, and they won't give you too many to do. Two times 1, 2 minus 2 is, oh, horizontal tangent. 2 minus 1 is -1, +1. 2 minus 0 is 2, and 2 plus 1 is 3. So see, wherever y is twice the x-coordinate, I have a slope of 0. +1, 45 degrees. +2, steeper than that. Oh, miss. +3, even steeper. Now that is not really that useful, right? This really is just an exercise in, do you know what a slope field is? Slope fields are most useful when they're larger. And I can look at a larger slope field and try to make some conclusions based on it. But for now, all you need to do is be able to draw without a calculator, right? So check your simple math like I did, right? If I'm making a mistake, ooh, 2 minus 1 is -1. No, Laura, no, it's +1. Stuff like that. Making note, things that I make note of are things like this. I do, while I'm working, I do note when I have horizontal tangent. I do note, right, here, I do make note of, gee, when was it when the slopes were negative? When was it when the slopes were positive? Just to start getting my brain thinking. And of course I think about this when I look about the derivative. Right? Just starting to train your brain to think in the slope field arena. So that's it. All you need to do is go to the Canvas work site, and under handouts you will see the slope field homework number 1, and you can see that it is, we just did number 32 here. We just did this one. Right, so your only practice is just drawing these other ones. Okay? So not too bad. Remember to study though for your quiz tomorrow. This won't be checked until Friday. And again, your quiz has no calculator on it, so don't worry about having the program or not having the program. Showing your work for Euler, separable differential equations of all types. Remember when you look for, did they say to get y by itself or did they not? the distance displacement with that little kicker of position in it, and again, since you don't have your calculator, focus on handouts 1 and 3 from that day and from the second day of that lesson, and then of course the book assignments where without position and displacement, without using velocity, acceleration, or whatever, just asking you to solve initial value problems. Okay? Have a swell rest of your day.